Alright, in today's problem, I will talk about Camelot. So in this problem, we have to understand how we usually do the Floyd-Warshall algorithm, and we will, instead of doing that, we will implement BFS and perform a similar algorithm on that, but only with a few pairs, not all the pairs of nodes. And we can simulate this board as a graph, and each edge or each pass will basically be a knight move. So here's the code. It's a bit long this time. And so first, after I received the input, I converted the rows and columns into to index with starting at 0. And also here I will reading the amount of knights that we have on the board. And first here we will check if the amount of knight is equal to 0. If it's equal to 0, then that means we don't have to move anything. The king can just stay on the board itself, and it would have already gathered every piece, which is just a king. So we'll just print out 0 here. Otherwise, we will do BFS on each of these grids, and every time we do BFS, we will come up with the distance from this grid to every other grid. And so here when we do BFS, we will first set the grid to itself as 0 because we don't have to make any move to be equal to this grid. And here there's the distance array. The first two part will represent the row and column of this original source, this starting grid. And the second two will represent the ending grid. And although it's only maximum 30 and 26, I just added a few to prevent any overflows. So here we will basically do the normal BFS just with a pair so we can record the coordinates. And so first we will have this initial grid at our queue, and we will get the front of this queue and check what other grids we can go to. So I wrote this other check function, which will just return if what we have is inside the board, because here we're adding the directions. There are 8 possible moves for each knight, and so we add these directions for each of these possible moves and check if this is inside the board, and also we need to check if this distance is equal to -1 or not. If it's equal to -1, this means we haven't visited it yet. So here in the beginning, I set everything in the distance to -1. And so if it's -1, we will set this to our current distance from the beginning grid into this RC. And we will increase that by 1 because now we've made an extra knight move to get from this grid into this grid. And now we'll add this into the queue so we can search this grid next time. So this will keep on searching. We will search through all of this, and every time we search through this, the maximum is R times C times R times C. So that is so the maximum is only 30 times 26, and this will not loop for too long. And here we will get the range, which I will talk about later. So this is the part where we will finally get the correct answer. So in the Floyd-Warshall algorithm, we will find an intermediate node and traverse starting from the beginning node to that intermediate node and into this ending node, and we check that distance. This part is basically the same thing, but we only check a few intermediate nodes. And so here, this will be the grid which we want to gather every piece as at. And we will first get the total distance that will be required to travel for all the knights. So here we'll go through all the locations of the knight and add this m, which starts at 0, by this distance ij to p first and p dot second. So this is the row number of the knight, and this is the column number of the knight. So if it's -1, this means we didn't find any possible ways to get to ij. from this using this knight, then this part I'll just set this to 0 and break this, and we will check if this f is equal to 1 or not. If it's equal to 0, then we know that there isn't a possible way here, so we'll just continue into the next position and check. But if it is 1, that means we can find the optimal solution in this position. So first, this is basically the part where we find the middle node and traverse through this node and see if this is a shorter distance or a longer distance. So here, this is our possible places of our king. So we can pick up our king with a knight and move the king along with the knight. And this is why I set these here. This is the starting row, this is the ending row, this is the starting column, this is the ending column. And I set this to the normal place at which the king is, -2, because if you draw this out, or if you try this out on a chessboard, you will see that if you move the king 3 times or more, then it's actually more efficient, or at least it will take at least the same move as at most the same move if you use the knight to pick the king up and move it. So the only way that when the king moves, it will be only optimal when it moves less than 3 times. So this is why we only check the range from the row number -2 and row number +3. Here it's +3 because I am using smaller than, so you can change this to +2 and use smaller than or equal to, but I'll just stick with this for now. And so we will check all the possible places at which the king could move to first, and this will get the distance for how much our king moved, and we can just find the maximum value for either of these, and so this will return how much the king moved. Then we can look through each of the knight and check if our knight can go to the place where our king is, well, where our king moved to. So if the current knight, so we check all the knights that we have. If this current knight can have the distance from xy to trtc, this means that it can move to this current position xy. Then we will find the minimum. We'll check the minimum one. So first, if we're trying to move the knight to the place where the king is, and then move the knight and the king along together into our final position ij, then we will add this distance. So first, we know that our king moved a bit, so we will add this into the place first, and we'll add we'll add the distance, how much our knight moved to get to the position xy, and how much it will move again to get to the from xy to the position ij, which is our ending node. And also we'll have to subtract away this ij to the real knight position. So we do this because now we've changed our knight's direction, and we don't want the original move anymore. Because now we have this new series of move, and so we'll subtract this away and add the distance, how much the king moved and how much the knight moved, and now we'll compare that with our optimal move. If this is smaller than our optimal move for the king and the knight, then we will set this to this current variable king, which I started at int max here, so we can always get a minimum 1. And then finally here, we will loop. So after we've looped through all the possible positions that the king can be, we will have an optimal king move for this ending node, ending grid ij. Then we will compare this with our answer again, which is also starting at int max here. So we will add our m with king. So this is our normal move. This will keep track of how much the other knights moved. And remember, since we subtracted away the amount of normal moves that this current knight TRTC have, so we won't have duplicates of this current knight move. So we'll also add how much the king moved, and so we will compare that with our current answer. If it's smaller than the current answer, we set the current answer to this, and we will loop through each of the possible positions, possible ending positions. And there are only 30 times 26 positions, so the loop will go through quick enough. And so at the end, you will loop through all of the positions, and then you can finally print out the answer.